Hello. Welcome to the second part of the morning session. Now we have Maissam Barkeshli. Who's going to talk about crystalline symmetry in topological phases of matter.
Thanks, Christian, for the introduction, and thank you to the organizers for inviting me to this great conference to speak. So I'm going to be talking about work. Mostly, I'm going to be the new work that I'm going to be talking about is with my former students, Naren Manjunath, and is my current student, and postdoc Ryohei Kobayashi, who's moving to the IES, or maybe he's already there. So this is a series of works that we've done over the years that I hope to be telling you about. So the story for me starts about 10 years ago, where we understood that gapped phases of matter in 2+1 dimensions can be characterized by what are called G-crossed braided tensor categories or G-crossed modular categories, together with one extra piece of information, which is a rational number, which is the chiral central charge. And the idea of this G-crossed braided tensor category is that you have the category with the G grading, and the objects in the CG, what they label symmetry defects. So in particular, they label codimension 2 symmetry defects in the system. And you need, so you have a codimension 1 G defect in space or space-time, and then it ends, and that endpoint is an object of this category. And you need this G-cross braided tensor category because you want to describe the algebraic properties of the symmetry defects, like their braiding properties and things like that, braiding and fusion and so on. Now, for our purposes, we can take G to be basically any kind of group, continuous or discrete, infinite or finite. In the continuous case, there may be some interesting questions to try to answer. And this is basically for bosonic systems, but if you're describing fermionic systems, there are some somewhat more complicated things that you need to think about, like supermodular categories and fermionic symmetry groups, and this was worked out a couple of years ago. Okay, but so now we have this theory, and you could ask, well, what should we think about now? And for me, I think there's two really interesting, outstanding fundamental questions. One question that I'm very interested in is, can we extract the topological data of a gapped phase directly from the ground state wave function? So you don't need to know anything else but the ground state wave function, and in fact, maybe just the ground state wave function on some simply connected patch of space. Can you extract the topological data? And if you can, to what extent is there an efficient algorithm to do so? I think this is a very fundamental question, and some of what I'll be telling you has some implications regarding this question. And the next very fundamental question is, the G-cross braided category was sort of designed to describe situations where the symmetry is unitary, and it's describing internal symmetries. Now, if you're thinking about real physical systems, the most common symmetries are actually crystalline symmetries, like translation symmetry, discrete rotation symmetry, reflection symmetry, and so on. So we'd like to understand what's going on with crystalline symmetries. And I think it's a very interesting subject because we've realized that there's a lot of interesting new physics that's hiding in very well-known models that people have been studying for a very long time. Okay, so first I want to tell you a little bit about how I think about crystalline symmetry in topological phases. I don't claim it to be the full story, but it's basically the understanding that we have that lets us make further progress. So we start off by thinking about the system on an infinite Euclidean plane. And I want to think about the symmetry as being characterized by a few different objects. We have our group G, then we have a group homomorphism from G into the isometries of the Euclidean group. So that determines which group elements are translations, rotations, reflections. And we have a Z2 grading on the group, which tells us which group elements are unitary or anti-unitarily represented. For fermionic systems, it's a little bit more complicated. There we have a fermionic symmetry group, which just means that you have a group which is a Z2 extension of a bosonic symmetry group. The fermionic symmetry group is the group that acts on fermionic operators. The bosonic symmetry group is the group that acts on bosonic operators. And the group extension by fermion parity is characterized by this second cohomology class, omega 2. So in the fermionic case, I would say that the symmetry is characterized by the bosonic symmetry group, this 2 cocycle, and then these group homomorphisms. Okay, so I think the most important point is that we want to think about how the crystalline symmetry acts at low energies. So if we have some lattice model with crystalline symmetry in the ultraviolet, and at low energies, typically that's going to be described by some quantum field theory. And we'll have different symmetries. The UV lattice model will have the symmetry G, and then the quantum field theory will have some symmetry of its own, which I call GIR. And that GIR will typically contain some internal symmetries and also some continuous spatial symmetries. So for example, in a very simple case, you might think that the infrared quantum field theory will have some internal symmetry across the Poincare group symmetry. But in general, it's going to be much more complicated than this. Now, the important point is that there's a group homomorphism that maps the UV symmetry into the IR symmetry. And the way that what this means is that if you're applying some symmetry in the UV, in the IR, it looks like a combination of an internal symmetry and just the vanilla spatial symmetry of the quantum field theory. So a nice example is just the 1D spin-a-half chain, which at low energies, if you tune the parameters correctly, will be described by SU2 level 1 West-Zuvino-Witten model. And then translation symmetry acts as just some internal Z2 symmetry. And there's a nice paper by Meng Chang and Nadi that has a recent discussion of these kinds of issues and much more. Okay, so then this also means that if you have a symmetry defect in the ultraviolet, according to G, then in the IR, it looks to the theory like an alpha of G symmetry defect. Okay, so then what's the consequence of this? The consequence of this is that, this suggests that if we know all the possible ways that internal symmetry can act in our IR quantum field theory, then we will also know all the possible ways that crystalline symmetry, the crystalline symmetry acts in the IR. So from this, I would deduce that if we want to understand all possible ways that translation symmetry acts in the IR, then it's good to just classify all possible ways that an internal Z to the D symmetry can act in the IR. And so then what we do is we'll couple the infrared topological quantum field theory for describing a gapped phase to some background Z to the D gauge field, and we call that background gauge field a translation gauge field. Okay, so there's much, much more to say about this. I've had many discussions with Nadi all the time, but I'm not going to go into more detail about what this means. This is sort of just how I'm going to treat the problem when we come to translation symmetries. Rotation symmetry, you think about similarly, although it has some more complication. For bosonic systems, then we would say that if you want to understand all possible ways that a ZM rotation symmetry acts, then you need to classify all possible way that an internal ZM symmetry acts in the IR. So this motivates us to introduce a background ZM gauge field, which we call the rotation gauge field. For fermionic systems, the situation is much more subtle. In that case, you have to deal with the spin statistics theorem. If you have a Lorentz invariant quantum field theory or some topological field theory, then fermions should have half-integer spin, according to the spin statistics theorem. And what that means is that if you, on the lattice, if you have some 2 pi over m rotation symmetry, and we raise it to the mth power, you get the identity, then you ask, how does that act on the fermions in the IR? That has to act by a combination of our vanilla rotation symmetry and our internal, and in some internal symmetry. And then the point is that because this is a half-integer spin representation, then when you do a 2 pi rotation, you get -1, and that means that this internal symmetry also has to have a property that when you raise it to the mth power, you get -1. And so that means that the effective internal symmetry in this case gets expanded to basically twice the size, and it's Z2M. The superscript F just means that the order 2 element is fermion parity. So similarly, if you have a situation where in the UV, your 2 pi over m rotations raised to the mth power is fermion parity, then in the IR, the internal symmetry has to have sort of the opposite property. So the effective internal symmetry becomes ZM in the IR. So these ideas motivate what these days are sometimes called in the literature the crystalline equivalence principle, which is just a statement that if you want to understand crystalline symmetries, then you should just understand quantum field theories with some effective internal symmetry. What is that effective internal symmetry? Well, it's not necessarily the same as the UV symmetry group, as I just explained. So more formally, you could say something like this. You have a correspondence like this. And for orientation preserving symmetries, you can write down a formula for the effective part here in terms of properties of the crystalline symmetry. So for orientation preserving symmetries, then you don't have to worry about what's unitary or anti-unitary. It's just everything maps over. But you have this interesting twist, which is exactly the twist that I described for rotations, which is just telling you that for fermionic systems, the ZM rotation symmetry becomes a Z2M symmetry in the IR. That's the physical content of this mathematical equation. With reflection symmetries, the story is much more complicated. We have some understanding of what's going on. I'm happy to talk about it offline, but I'm not going to say anything more about it. The formulas, we have some formulas for how the correspondence works, but they're kind of counterintuitive, actually. Okay, so now equipped with this understanding, now I want to go and analyze a problem which is of relevance in condensed matter physics. So in particular, let's think about a gapped topological phase of matter in 2 + 1 dimensions, which is described by U1 level M Chern-Simons theory. So this arises all over the place. There are fractional quantum Hall states, there are fractional Chern insulators, quantum spin liquids, and it's been a topic of great interest for the last 40 years to understand the properties of these things. Now, if this arises from a lattice system, then we will typically also have, at least in an idealized model, also a U1 global symmetry, or translation symmetries, rotation symmetry, and often we also will have some magnetic flux per unit cell, so the translation symmetries are actually magnetic translation symmetries. So the question then becomes, what's the classification of phases, and then how do we distinguish them? And then, more interestingly, are there new quantized responses and invariants that we can measure in experiments or in numerical simulations? So this is what we want to do. So I'm going to mostly focus on a simple case, which is the case of U1 level 2 Chern-Simons theory. And first, let's just talk about, we have some Z4 rotation symmetry. Try to understand what happens. Okay, so before I do that, I told you that, well, I'm going to just treat the crystalline symmetry as some effective internal symmetry. So now I have to use the formalism of internal symmetries, and that was the G-cross braided tensor categories. So I'm going to spend a couple of slides telling you about the main aspects of G-cross braided tensor categories that I'm going to use in this talk. Basically a quick review. So we have this G-cross braided tensor category, which has this G grading. Then, and the point is that if you start with a modular tensor category, which is the C0 part of this, and G symmetry acts on it, then there's multiple inequivalent G-cross braided extensions. And the way that you can parameterize the different extensions is in terms of group homomorphism from, sorry, this row is different from the row I used earlier. From G into the group of braided autoequivalences, we have another layer which we call symmetry fractionalization, which dictates how the anyons carry fractional symmetry quantum numbers. And this is parameterized by a set of symbols, which graphically we show like this. We have these codimension 1 G defects, and you can push it through the vertices of fusion diagrams, and you get some matrix generally that acts, which is this U symbol. Or you can have a junction of symmetry defects, and you pass some anion line through it, and you get a phase. So this data characterizes symmetry fractionalization, and it's the different possible choices of this data is classified by this particular second cohomology group, where A is the group of one-form symmetries, the group of abelian anions. There's a lot more data. I'm not going to tell you about it. It would take a long time, but you have also like G-graded F symbols, G-crossed R symbols, and the different choices that you can have are parameterized by an element of this third cohomology group. So the next important thing for my talk is that there are also G-crossed modular S&T matrices. So if you put the system on a torus, then you can have branch cuts G and H along the two cycles of the torus. So G and H have to commute. And so you have a space of these twisted sector states on a torus. And that I'm going to denote by this VGH. And so the S and T modular transformations now mix up the boundary conditions here. So we have SGH and TGH. And we can derive expressions for these modular S and T matrices in terms of this U symbols and eta symbols that I showed in the last slide, and all the other usual data that you're familiar with. Okay, so the expressions are quite different than what you already know from modular tensor categories. And interestingly, these expressions are not even gauge invariant. So if you want to know gauge invariant data of the theory, you have to take special combinations of these S and T matrices.
Question?
Yes.
The gauge covariant?
Gauge covariant. So yeah, there are gauge transformations, and there's very special gauge transformations in this theory, and these things transform in a very well-defined way under these gauge transformations. Okay, so now let's come back to our U1 level 2 with Z4 rotation symmetry. First, I'm going to describe it using Chern-Simons theory, good old-fashioned Chern-Simons theory. So we have our U1 level 2, the A is our dynamical U1 gauge field. I'm introducing this rotation gauge field, and now I can couple the background rotation gauge field, which is a Z4 gauge field, to my theory. And I have these two new parameters I need to think about. These are two new symmetry-enriched topological invariants. S is, we just take to be 0 or 1, mod 2. This determines the symmetry fractionalization of the theory. So this corresponds to that H2 class that I was talking about. Physically, it tells you that the anion of this theory, which is called the semyon, carries a Z4 charge, a fractional Z4 charge of S over 2. Physically, because Z4 corresponds to rotations, this means that you can get a fractional orbital angular momentum for the anion, in addition to its usual topological spin. Then we have this other parameter K, which can take 4 possible values, and that corresponds to basically stacking an SPT on the system, which corresponds to this H3 degree of freedom. So then the question becomes, well, how can I detect?
I have a question.
Yes.
Here. So since this omega is kind of inside the kind of spin connection, if it was working the continuum, when you write this SPT, you think of this in the sense of like a gravitational inflow for anomalies, or it's a different thing for you?
No, so here I'm thinking omega I'm just thinking of omega formally as an internal gauge field. Now, there will also be a spin connection. And remember, there was this group homomorphism that said that the UV symmetry maps into the IR. So that would tell you that you should kind of tie the internal gauge field to the spin connection. So every time you have like a singularity of the spin connection, which means you're on a cone, that should come with the holonomy of this internal gauge field. So they're kind of tied together.
If you turn on this guy, you are changing the chiral central charge a bit in your idea, or not?
No, you're not changing the chiral central charge. The chiral central charge is unchanged. Okay, so the thing that we would like to understand is what does this mean? How can we measure it? What is its physical consequences? How to measure it in a microscopic model? Okay, so that's where this story of partial rotations comes in. So the idea is that we can measure these quantities S and K from the ground state by taking ground state expectation values of partial rotation operators. Okay. So first let me tell you what the theoretical prediction is, and then I'm going to tell you the derivation, and then I'm going to tell you the experimental, i.e. numerical evidence that it works. Okay, so we're taking this U1 level 2 system. So this is the theoretical prediction. You consider your system on some big, whatever, patch of space. You consider a subregion, which is a disk. And you take the pi/2 rotation operator, and you restrict it to the disk, and you take the ground state expectation value. Because you've restricted to the disk, then when you do the rotation, you're gonna mess up the boundary. So you're gonna get some exponentially decaying amplitude, but you'll also get a phase. Now, we're going to take that phase, and we're going to take it either modulo 2 or modulo 4. We take it modulo 2 if that S parameter that I showed you was 1 mod 2, and we take it modulo 4 if S is 0 mod 2. Now, my claim is that this theta is an invariant. Okay? This is invariant, and it basically detects S and K. So this is the theoretical prediction that we derive. This K here is given by this complicated formula. It involves a piece which involves the symmetry fractionalization, and then involves a piece which depends on that K integer, which is called the SPT contribution, and there's just some extra piece that doesn't have a reason to be there aside from the fact that it pops out of the calculation. And this bracket means you take mod 2. Okay, so the key reason why this works is basically, it goes back to an observation from Lee and Haldane in 2008, which says that if you look at the entanglement spectrum, which is the spectrum of the reduced density matrix on this disk, it happens, the low-lying part of the entanglement spectrum happens to match the boundary conformal field theory of the system. And then the symmetry operation acts in topologically distinct ways in that boundary conformal field theory in a way that we can analytically compute. So, so I'm going to tell you how that calculation works, but note that this is all from a ground state wave function. So this is an example of what I was telling you earlier, where given the ground state wave function, it looks like we can extract invariants that are predicted by the G-cross braided tensor category or Trinh-Simons theory. Okay, so the theory of partial rotations, this low-lying part of entanglement spectrum matches the boundary CFT, that's what I said. So Lee and Haldane showed this nice plot where this is the entanglement spectrum, which is the log of the spectrum of the reduced density matrix. The low-lying part here matches the boundary conformal field theory. So basically what we do is we just take the density matrix on the disk and approximate it by the conformal field theory density matrix. And importantly, the conformal field theory is actually at high temperature. So here C is the correlation length, which you should think of as being small, and L is the circumference of this disk, which you should think of as being large. And there was a very nice paper by Xiaoliang Qi and collaborators that gave a nice physics proof of why this is the case. Okay, so the theory of those partial rotations, so we want to calculate this partial rotation expectation value. We're going to reduce it to a computation in conformal field theory using this correspondence. And then the point is that this CM rotation acts in the conformal field theory by a combination of the vanilla spatial symmetry, which to the conformal field theory looks like a translation symmetry, combined with an internal symmetry. So e to the I QM is the internal symmetry, and e to the IP is the translation symmetry along the CFT. H is just the CFT Hamiltonian. Now the bulk of this disk is in the trivial topological sector, so we use just the identity character, the character for the identity for the vacuum sector in the conformal field theory. And then the point is, because we have this e to the I q hat, it's like having a symmetry defect in the time direction. That's labeled by this 0, 1. So we just have this expression for the partial rotation. And then what we'd like to evaluate this and get a nice answer out. And it turns out that you can do a series of modular transformations, a series of G-cross modular transformations to make the time direction much larger than the space direction, which then gives you a nice approximation for the characters. And so those series of G-cross modular transformations is this S t to the ms. And then at that point, the time direction, which is the imaginary part of the modular parameter, becomes large. Then the main contribution is from the lowest weight state of the conformal field theory. So you get this expression for the character. And then now you have to insert the expressions for the G-crossed modular S&T matrices that I showed you earlier from the G-cross braided tensor category. So you plug that in, and then you get this interesting complicated expression. But importantly, it all depends on universal data from the G-cross braided tensor category. Okay. Now, you can make further progress and relate this to the Trinh-Simons theory, because it turns out that when the symmetry does not permute anyons, then you can simplify it, and you simplify it to an expression that looks like this, where now S is just the ordinary modular S matrix of the modular tensor category. This e to the 2 pi I LB is the fractional orbital angular momentum of, LB is the fractional orbital angular momentum of the anion B, and that's given by this expression. And then IM is given by this expression. So importantly, these two things have the S and K in them. Okay, so now this derivation explains the formula that I had given earlier. This is how we derive that complicated formula that I had shown. You just evaluate this in the special case that we're thinking about, and you get this formula. But if you remember, there was another aspect to it, which is I said that we have to take that phase, this K, either mod 2 or mod 4. And where that comes from is that in the G-cross braided tensor category, we can always relabel our symmetry defects with anions. So we have this relabeling that we can do. And under this relabeling, these parameters that I showed you actually change. So in particular, if S is 1, this IM will change by -1. Whereas if F is 0, IM does not change. So that explains why we have to take this modular reduction in order to get an actual invariant. So, that's a theory for this simple example. And now we can come to the confirmation of this using numerical simulations. Now, it's an old subject that if you want to describe like a system, if you want a ground state wave function for a system described by U1 level 2 Chern-Simons theory, there's this famous construction called the projective construction or parton construction or slave particle mean field theory, whatever you like, Gutzwiller projection. And the idea is that you can get the many-body wave function, you can get a model wave function by taking free fermion wave functions and just projecting them together. So in this particular example, psi1 and psi2 will be many-body wave functions for free fermion systems that are described by U1 level 1 Chern-Simons theory. So alternatively, condensed matter physicists would say these are wave functions for Chern insulators with Chern number 1. Now, these free fermion states, you can come up with any free fermion model you want to get a model wave function for these free fermion states. So in particular, we use this Harper-Hofstadter model, which is just spinless free fermions on the square lattice with some flux through every plaquette. And then we do Monte Carlo. We just calculate this expectation value using Monte Carlo. And every color here is a different value of the flux in that Harper-Hofstadter model. Every dot is 1,000,000 Metropolis Hastings steps. And then we average over all the same colors, and we see, and the axes, this is the real part of this expectation value, and this is the imaginary part of this expectation value. And then the key thing to look is that when you look at that phase K, then indeed it's quantized, but you can have these jumps as you tune some parameters, and those jumps are exactly the change by -1 that I was talking about, which is why you need to take that modular reduction to get an invariant. Anyway, you can extract an invariant from this, and it agrees with the theoretical prediction. And actually, it goes even further. The free fermion states have their own crystalline invariants, which we know how to calculate. There's a whole story about that I don't have time to tell you. And then using that, we can predict exactly what we expect for every wave function, and the theory matches the numerics very well. Okay, so then we can continue. We can add U1 symmetry, and then the main thing, we get all kinds of new invariants. And now we have to do a partial rotation where we do a partial C4 rotation and a partial U1 rotation. And then the formulas just become more complicated, but it's the same basic idea that you can go through. And again, we do numerical Monte Carlo calculations that confirm the theory. And then finally, you can add magnetic translation symmetry as well. And then you would want to write down a Chern-Simons theory that has background translation gauge fields, rotation gauge fields, and also the U1 gauge field. And it would take a whole talk to explain how to do that. But if we can just calculate the cohomology groups for the G-crossed extensions, and we get a whole host of new invariants. And the upshot is that we can actually extract every one of these invariants by doing ground state expectation values of partial rotations. But the key is that you need to, when you have translation symmetry, you need to consider vertex-centered rotations and also plaquette-centered rotations. So if you do ground state expectation values of vertex-centered and plaquette-centered rotations, combined with the U1 rotation, you can kind of get everything from the ground state. Okay, so let me end there. I'll just leave the summary up. So thank you very much.
Any questions?
So if you have Z2 times Z2 acting on unit level 2, I guess for some fractionalization class, there's an H4 anomaly, right? So can we see that? Can we extract that information as well?
Can you extract it from what, from like the ground state or something?
Yes, and also maybe can we see it as some anomaly from UV, including some spatial symmetries? But now we have Z2 times Z2.
So the Z2 times Z2, it wouldn't come from the crystal symmetry, so it would have to be on-site symmetry. And then your lattice system would itself have to live at the boundary of a higher dimensional system. You could ask, if I have this ground state of this whole higher dimensional system, including the boundary, can I extract the symmetry fractionalization data just from the ground state? And that's an interesting question. I haven't thought about that, but I think the answer should probably be yes.
Thank you.
Can you also include orientation reversal into this framework? So this crystalline correspondence principle.
Yeah, so if you, I showed this formula for the crystalline equivalence principle when you have reflection symmetries. And so this formula, we have to assume that it's always true in our context, and we have a lot of evidence that it is true. But if we use this, then we can include reflection symmetry in the classification. And then you can ask, can you extract the invariance from some kind of partial symmetry operations on ground states? And the answer also seems to be yes. We have some limited results on that. Like one thing that we looked at recently was the case of RT symmetry, reflection combined with time reversal. And there we showed that the classification using this equivalence principle works, and that you can extract the invariance from the ground state. But we only did that for invertible states.
Thanks.
Any more questions? Okay.
So you showed us an example of a construction where you began with the C equals 1 lattice state and then the part on construction. But now supposing I play the game differently, I start in the continuum with the usual symmetry and I put on a weak periodic potential with some enormous wavelength, right, which in principle breaks the symmetry. Mm-hmm. Do I get, I mean, there at least I know how to think about it in traditional terms. I've got quasi-particles, they'll drift along, sort of equipotential contours. So is there a way of understanding your results from that, or is that a different limit?
No, you can understand in that context. So in the continuum, you'll have a continuum translation and rotation symmetry. And you can actually do the same formalism. You can input, instead of inputting like the discrete rotation symmetry into this formalism, just input a continuous SO2 symmetry into the framework. And then what you'll recover is actually are all the Wen Z terms that Xiaogang and Tony Z wrote down back in 1991. And
it's the symmetry breaking I want to understand, which is I want to understand your formula starting from that.
Yeah, but that's so what I'm saying is that in the continuum, you will have these invariants like S and K, but S will be an integer and K will be an integer. And then when you add a weak periodic potential, now S will only become well-defined mod 4. K will only be well-defined mod 4. So the invariants are already there in the continuum. Then when you add the periodic potential, you'll just make the invariance well-defined modulo some smaller number.
But I should, again, I mean, as an old-fashioned condensed matter physicist, I would just say, I had one quasi-particle and a periodic potential, and I can do a semi-classical understanding of their wave functions, and they move around, right? So in that picture, where I have an explicit picture of existing quasi-particles simply moving in a periodic potential, what are the invariants? What's the new spin?
In that case, there's a question of what is the orbital angular momentum of the quasi-particle. Mm-hmm. And that has two contributions. It has a topological contribution, and then it will have some extra contribution from the symmetry.
Okay, so if I rotate about the center of a unit cell, now I have to...
Yeah. Well, you have to rotate you have to take the quasi-particle around some curved surface you have to rotate the quasi-particle basically to see this orbital angular momentum.
All right, there's a long ago paper I wrote with Steve Gervin.
I was about to say you wrote a paper on this.
Okay, so let's take Maissam again for the very nice talk.